Okay, so a second place where something like this happens, where the data that you have kind of magically encodes things that you can't see necessarily, is in a subject in math called Fourier analysis. So imagine I have a signal coming that at every time step looks like this.
Alright.
So, and this just looks a lot like noise to you. And it just looks like random dots because, well, in this case I really have put random things down. There's something in calculus called Fourier analysis that allows you to pick out signals out of this if they're there. And it's kind of the same thing where previously for Cramer's rule B encoded the solutions, and if you looked at it the right way. The signals that you see coming into our house, either like on our cell phones or in cable, or where's another situation where you think there's signals sort of coming through the air that a device picks out the signal?
The internet?
Yeah, the internet, yeah. Good, or a radio or something like that. It gets all this feedback, or all these things coming into it, and it picks out a signal. And it's just a very simple idea that we're going to look for signals of the form, let's say cosine kx. And the interesting thing is if our noise looks like a sum of ak times cosine of kx, from k equals, sort of 0 to infinity, so in a cosine wave, that's k equals 1, k equals 2 will have double the frequency, and etc., times some constant. The neat thing we can do is, much like we took the determinant and we had zeros magically appeared, we can multiply this by cosine of, let's say, just cosine of x, and then integrate it over the full length of our signal from, let's say, 0 to 100 or whatever. I'm oversimplifying a little bit. But an amazing thing happens here. When I take the integral, I guess I better make it 100 pi or something so I get the right cycle length. When I integrate cosine of nx times cosine x, well, actually I can do it in general times cosine mx for m not equal to n, I always get 0. And when they are equal, I end up getting cosine squared nx dx. And why is this integral not going to be 0?
Because cosine squared is always positive.
Yeah, cosine squared is always positive.
Or 0. Or
that's right. It's never negative. Good point. It could be 0, but it's never negative. So this, if m equals n, is not equal to 0. So all of a sudden, by just doing a simple multiplication by a cosine of a specific cycle, all of a sudden the only thing I end up seeing is that signal. So I'll get a non-zero integral if a cosine of mx signal is there. And otherwise I'll get 0. And so this allows me to pick out signals out of noise. And it's basically exactly the same idea. I have this linear sum. I shouldn't say it's exactly the same. It's very similar. Of ak cosine of kx. And I want to pick these out, just like I pick the x's out of the b's. And I just do a clever multiplication. I get zeros on every part except for one part. And I'm going to show you, again in Mathematica, what this looks like and why it's so fascinating. Because I'm going to show you some examples where you visually can't see the signal. And this mathematical technique, which is just the simple integration idea, pulls out the signal, or it tells you that there's a signal there. So let's take a look at that.